Go ahead and start and just introduce myself in the seminar series. My name is Sid Mitra. I'm a professor at East Carolina University, and I'm the chair of the Eastern North Carolina chapter of the American Chemical Society. We have been stifled by COVID, but we haven't been stopped completely. And this is the seminar series is part of our attempt to continue doing science and continue getting chemistry out to our constituents out throughout the eastern part of the state. So we're very excited for you to join us. This seminar series, specifically the Diversity in Chemistry series, is a brainchild of one of the PhD students in our program, in our region, Malcolm Barnard, and I will let him take over doing the introductions. And you get emails from me occasionally to the chapter, and so stay tuned because we have some fun events coming up. Malcolm?
Thanks, Sid. Hi all, my name is Malcolm Barnard and I'm a PhD student at University of North Carolina's Institute of Marine Sciences here in Eastern North Carolina. Welcome to our third seminar in the Eastern North Carolina section of the American Chemical Society Diversity in the Chemical Sciences seminar series, funded by a local section sustainability programming grant from the American Chemical Society Committee on Environmental Improvement. Before I introduce our incredible speaker for today, I want to talk about a few Zoom seminar housekeeping items. If you have questions, please type your questions in the Q&A portion below, and they will be answered at the end of the seminar, unless Amari would like to address them at the time. Additionally, this seminar is being recorded and will be available after the seminar on the Eastern North Carolina ACS YouTube channel, which I will put a link to in the chat following this introduction. Without any further ado, it is a great honor to introduce today's seminar speaker, Amari Walker, who is a PhD candidate in civil and environmental engineering at Duke University with a graduate certificate in college teaching in the Ferguson Lab. She received her Bachelor's of Arts in Marine Science at University of California at Berkeley in 2016 and her Master's of Science in Civil and Environmental Engineering from Duke in 2019. Ms. Walker investigates the fate, occurrence, and transformation of plastic additives within aquatic environments. In particular, her dissertation work focuses on endocrine disrupting chemicals like bisphenol A, also known as BPA, that are of concern to human health and the environment. Alongside her PhD work, Amari uses her science communication-based YouTube channel to share information about plastic pollution, microplastics, and chemicals associated with these consumer products. I will also share a link to her YouTube channel in the chat following this introduction. Today, Ms. Walker will be talking with us about release and transformation of polymer additives into aquatic systems from plastics and nanocomposites. Please welcome our seminar speaker, Amari Walker.
Thank you, Malcolm, and thank you all for having me here today. All right, let's get to it. So, as Malcolm said earlier, my name is Amari Walker. I'm in my 5th year at Duke studying environmental engineering, and I really enjoy studying chemicals coming out of plastic. Some of the other things I like to do also include being a Duke law and policy consultant, studying plastic policy nationally and locally, along with being a microplastic science communicator through the YouTube channel that was just indicated before. So I really like plastic, as you can see, but why? Well, it's a really emerging issue because we've been using it since the 1900s. We've been exponentially producing plastic, especially after World War II. And one of the biggest issues with it is that while we use it for everything because of its utility, the fact that we can mold it into any shape or need for plastic packaging or infrastructure or even our consumer products, a large majority of that plastic is actually single-use plastic that ends up being discarded into our environment. So about 5.8 billion tons in 2015 in particular ended up used for on an average less than 6 seconds, and then ends up accumulating in our landfills and sometimes even in our marine and terrestrial environment. And so I think they've predicted somewhere around 1 to 2 million tons of plastic that is faded to the ocean coming from environments like our rivers. Along with, by 2050, they're predicting around 1,200 million tons to end up in landfills and our environment because plastic is so ubiquitously used in our everyday lives. Now, it's not just that plastic is, being used in exponential amounts, but it's also the fact that the degradation of plastic is, it takes a really long time. It can span from, tens of years to hundreds of years. And a lot of that degradation is dependent on the plastic type. But when it degrades, it turns into sometimes microplastics. And so microplastics are defined as plastics that are smaller than 5 millimeters. And they can be classified by either being primary, which are plastics purposely made that small, found in things like face wash or body wash, which are mostly banned, especially in the United States, to being in industrial paints. Now, secondary microplastics they come from the breakdown of larger pieces of plastic, and that's from mostly environmental processes. And all of these microplastics can be characterized by the variety of shapes and fragments they form, their size ranges, and even the colors. So what about secondary microplastic formation? That can occur from things like water, hydrolyzing the surface of the polymer, wind or air causing oxidation on the surface, to photolysis coming from UV light, to even mechanical abrasion that ends up fragmenting and forcing the plastic to become brittle, break apart, create larger surface area, and release micro and even sometimes nanoplastics, which we're not going to get into.
Hey, Mari, you want to turn on the subtitles?
Yes. Thank you. When they're releasing these microplastics, or plastics in general, can actually have quite a number of different combinations of chemicals within them. And these chemicals are used to aid in the functionality of the plastic, but also in the longevity and the aesthetics. And so some of them include monomers, which are the basic building blocks of the plastic itself, to plasticizers used for the functionality, the rigidity of the plastic, to even the dyes and colorants for the aesthetics. And so there's hundreds of different combinations that can happen with these chemicals. And the big question is, while they're great for enhancing the lifespan of the plastic while you're in use of it, it can be harmful when they end up in our environment, in our water. And so the question is, what are the hazards to that? And some of them include being endocrine disruptors, so affecting reproductive decline, being carcinogenic potentially, mutagens, toxic to aquatic life, persistent and bioaccumulative. And some great examples include even the perfluorinated chemicals that are a new emerging contaminant class that are also found within polymers and sometimes even used as anti-slip agents when you're actually forming these polymers, to being the films used in compostable plastics to prevent the leakage of your food products out of the containers. So when looking at these hazards, there have been a couple studies done, especially for plastic packaging, of around 4,000 chemicals that they suspect to be associated to plastic packaging. Around 98 were suspected human health and environmental health hazards, matching those on the list. And great examples include bisphenol A, which is a suspected endocrine disruptor. And what's interesting is, when they substitute those compounds out, sometimes they're very small changes to the molecule that can be more or even less toxic, like this bisphenol F. To the dibutyl phthalate, which is another plasticizer used in plastic and is also known and warned about in Prop 65 as being a potential carcinogen, cause birth defects, or other reproductive harm. And so you see those warnings about those phthalates in hotels in California. So what else can we find in our plastics? Well, other things include nano fillers. So these are what make nanocomposites. Carbon nanotubes in particular are used in consumer products to improve the material properties of the polymer, such as the electrical and thermal conductivity. And those can also end up in our environment or in our landfills and release polymer additives. And so those chemicals associated to polymers like BPA, highlighted before, tert-butylphenol, and nonylphenol, can all be released into our water and are known endocrine disruptors. So how do they end up in our water? What's the process? Well, we suspect that weathering the polymer might play a factor in the release of these additives. And weathering can include those I highlighted before to even make microplastics, like light, increased temperature, natural organic matter that can form reactive oxygen species to oxidize the polymer, to even mechanical abrasion that creates a larger surface area to release these polymer additives, along with pH, which can drive acid or base catalyzed hydrolysis on the surface of the polymer. And so these additives are battling not only internally in the bulk structure of the polymer, where they're trying to migrate to the surface of the plastic water boundary, but also just dissolving into the water is another chemical issue that they have when they're being released. So what is my research? My research is looking first at nanocomposites and how they interact with polymer additives placed within them and how they're released in aqueous environments. And then looking at the release and transformation of polymer additives when you're exposing them to different environmental stressors, including laboratory studies on the bench and mesocosm leachate studies that can change anything from light, temperature, pH, and NOM content. And that can be highlighted through this visual, all my three aims for my PhD. And so that the first one was the polycarbonate and the epoxy nanocomposites that are highlighted in that landfill. So they're put in simulated landfill leachates and simulated freshwater environments. To my second aim, looking at polypropylene and polyurethane microplastics in simulated, in a mesocosm environment for freshwater. And then my third aim, which we won't get into in this conversation, but it is looking at commonly found beach plastic and their release of chemicals from them that are potentially endocrine disrupting in the stomachs of birds and fish, at least simulated digests. So the first aim, this is the influence of carbon nanotube loading and environmental stressors on these polycarbonate and epoxy nanocomposites. And the hypothesis for this is that first, carbon nanotubes are likely to act as a sorbent. They've been shown in the literature, used in even water treatment centers to absorb contaminants, and in experimental studies to absorb even bisphenol A. And so we believe when you add them into the polymer, they're likely to actually decrease the release of these additives into the water because they can act as a secondary sorbent. The second hypothesis is that cryomilling the plastic is going to create microplastics first, and that will also increase the release of additives because you have a larger surface area. And then finally, these environmental stressors like UV light, high temperature, and natural organic matter are likely to also increase the weathering of the polymer surface and release plastic additives. So the experimental goals for this project include looking at these two plastic types, polycarbonate and epoxy, and they are both made with the monomer bisphenol A, and then loading different concentrations of carbon nanotubes ranging from 0 to 1%. Next is to actually weather these polymers or place them in environmental stressor conditions, whether we're varying the temperature, the pH, what the surface area available, in measuring the release of these two compounds, bisphenol A and 4-tert-butylphenol. Within the experimental design for first the polycarbonate was first dissolved in chloroform, and then 2% weight of bisphenol A was added. And then varying concentrations from 0 to 0.3% carbon nanotubes were placed to make these discs. And these discs were either pre-treated with UV light for 5 days or not, and then leached for 5 days to measure bisphenol A. And those included just different pHs and different temperatures and different NOM content in the water. For the epoxy, this was a hardener and a resin mixed in with carbon nanotubes in concentrations a little higher, ranging from 0 to 1%. And while we made discs similar to the polycarbonate, this got extended UV light exposure to 14 days. And then these discs were also cryomilled to create microplastics in sizes around 150 micrometers in diameter, and then also underwent the UV exposure or not prior to a 5-day water leaching. And for the epoxies, this was all in simulated freshwater and varied temperatures as well. So first, looking at the polycarbonate data, this on the left is BPA released in micrograms of BPA per gram of polycarbonate. You can see for the trend over 5 days that the amount of BPA is increasing over time, doesn't seem to stop as far as for 65 degrees. And then in the lower temperature, once it reaches the first day of leaching, it seems to stop there, it doesn't seem to increase. For the comparisons between the amounts, there's a pretty significant amount released from higher temperatures. And when we look at the different carbon nanotube concentrations, the square is the plastic with no carbon nanotubes, and it seems to release around similar amounts as the 0.05% CNT. However, the higher concentrations in the triangle and the diamond seem to release less, and so also following the trends that we were expecting. But at low temperatures, there seems to not be a lot of significant differences between them all. And this is all at pH of 8 in simulated freshwater. When looking at the different treatments in the top right, that's just the temperature, and then along the x-axis, those are the differing increasing CNT concentrations at the final day of leaching. It just reiterates that temperature was the most significant factor for the release in that treatment. Along the bottom, also you can see for pH ranging from 2 all the way to 8, that the high pH was also the most important for release of these additives, or for bisphenol A. And then for natural organic matter, there was no significant difference between the two treatments with or without natural organic matter, and that is potentially because it was done in the dark, and that's not as likely to create those reactive oxygen species that might change the situation. And finally, the UV light, there seem to be no significant differences between the two treatments, except for when you get higher in CNT concentration. But that may be due to the fact that there was not as much UV light time or just leachate time to see a lot of significant differences between the two treatments for the polycarbonate. And then similar to before, there was just a trend of with increasing carbon nanotube concentration, there is a decrease in the amount of BPA released in these polycarbonates. When looking at the epoxy polycarbonates, these are on the left are all the figures for bisphenol A, and then on the right are all the tert-butylphenol concentrations over time. It's a little different than the polycarbonate, which was just steadily increasing over time. For these, by the time they hit the first few days of leaching, there seems to be a lot less released, well, just the same amount being released over time. And we did a few more temperature treatments, including a 45 degrees Celsius. And there seemed to be some differences between temperature treatments for the disc, but for the cryo milk plastic that made microplastics, it seemed to be a lot less temperature dependent, especially once you UV exposed it as well, which are in the dark filled shapes. So temperature and UV exposure were pretty important. The next thing is looking at what are the trends with increasing carbon nanotube loading from 0 to 1% CNT loading. And that also showed no matter 25 degrees Celsius or 65 degrees, that there was a trend of decreasing amounts of those additives with increasing carbon nanotube loading, especially more relevant for the tert-butylphenol additive itself. The other thing to note is that there is a lot more tert-butylphenol released than bisphenol A, no matter what treatment. And what we suspect, or what I hypothesize, is that it's because of the total available concentrations of the two. There's a lot more tert-butylphenol available when you do extractions of the polymer, and tert-butylphenol is much smaller of a compound than bisphenol A. It's about I think BPA is about 1.5 times larger in mass than tert-butylphenol. So there may be some hindrance for migration with those two. And also the UV exposed cryo milk plastic was the most significant for release of these compounds, followed by the UV exposed disc and then the cryo milled epoxy. So some of the findings for this work are that the processes that we expected to actually weather the polymer did end up exacerbating the release of these additives, including higher temperatures, UV light that could photooxidize the polymer, and increasing the surface area by creating these microplastics increased the release of both tert-butylphenol and bisphenol A. Secondly, carbon nanotubes were decreasing the release of these additives over that time, and we hypothesize that they're acting as that sorbent for the polymer. And finally, I think that this study has some interesting implications for the study of monomeric additives that make up plastic and just additives in general, and might encourage better green chemistry practices, because both of these additives are potential endocrine disruptors, and it would be pretty problematic to see them released into our environmental waters. So next, in the second aim, I'm using high resolution mass spectrometry to understand additive leachings from polyurethane and polypropylene microplastics. So why? Well, the aim for this is to really understand the environmental fate of plastic that's used to protect coastlines. And in particular, plastics have been used to prevent coastal erosion. And the question is, once they degrade and form into microplastics and end up in that water, where are they going to go? What's the fate of those microplastics? And then what's going to happen to the additives that you find within these plastics, and how are those chemicals likely to transform over time and with just different environmental conditions? So we did a mesocosm project. This is just a schematic of the boxes found in the Duke Forest, and they're about 3 feet deep, 12 feet, wide, and they house everything. They're supposed to be microenvironments where we can dose contaminants to monitor over long time spans. And so with this experiment, we dosed a polypropylene and a polyurethane microplastics into individual boxes into the water to amount to about 50 milligrams per liter of microplastics in water. And then we took water samples, sediment, snails, plants, fish, and at least for this conversation, we'll be talking about the water and the sediment for the analysis. The time points taken were over a year. There were 5 time points taken, and the conditions were similar to most of Durham, North Carolina. The water was kept around 18 to 25 degrees Celsius, and a pH of around 8 in the mornings when we were actually doing those sampling time points. Now, to complement this mesocosm study, because there's a lot of variance in the environment, I also did a laboratory controlled bleaching experiment, and that included taking the plastic and UV exposing it for 2 weeks prior to bleaching, along with plastic that was not UV exposed, in concentrations around 10 milligrams per milliliter, so much higher, but important for direct injection on our instrument. Sample conditions were kept around 20 degrees Celsius, so similar to the mesocosm, in the dark and in simulated fresh water. The time points for this, instead of a year, we did around 3 months and took more time points to really understand the kinetics and the transformation over time in just a water sample. So there's quite a few different samples. There's the plastic itself that was extracted in methanol, the water samples from the mesocosm that underwent solid phase extraction, to the laboratory leaching study where we just took 1 milliliter out and did direct injection after filtering the water, to the sediment, which was freeze-dried, and then some of it was used for isolation of microplastics by hand and eye, and then others for chemical analysis where the sediment samples were extracted and then cleaned up using solid phase extraction in 500 milliliters of water. The analysis of these samples with the purpose of doing non-target analysis to identify those chemicals and transformation products was done on the Thermo Fisher Orbitrap Thermo Fisher Orbitrap Fusion Lumos mass spectrometer, and it was also using HPLC with acetonitrile and water with 0.1% formic acid. So the goal was to keep the mass accuracy below 1 part per million so that we could do really good identification of these compounds. And that included a spectral library matching with libraries like from NIST, MZ-Vault, and MONA, doing in silico fragmentation for those that to further confirm these compounds, or to provide new identifications for those that weren't in our software, and then identification with standards that we could order as much as possible. So for the sediment samples in particular, this is just a diagram of the microplastics that we could identify by eye, and that's by weight, and then also by microplastic count. We could see that for both the polypropylene and the polyurethane, there seemed to be an increase in the number of what we suspect to be microplastics over time, especially the first 6 months. And so it brought to questions maybe the fate of those microplastics might take similar time spans to reach the sediment of the mesocosm. But I think the water was also going to tell a very important story. So the analysis of the extracts of the plastic and the leachates, we were able to identify around 400 different compounds within those samples. And you can see on the right the number of compounds found by retention time and mass to charge ratio. And within the laboratory leaching studies, somewhere around 200, 300 compounds identified. And there's quite a big difference between those found within the polypropylene versus the polyurethane samples. For the compounds that had a large match to the spectral libraries, there were a lot fewer, around 40 in the mesocosm and around 32 in the laboratory controlled studies. So when comparing compounds in the water samples versus the extracts of the solvent, it was important to notice that we found some antioxidants, some things that we suspect to be monomers of the polyurethane, biocides, and this UV inhibitor, the 2266 tetramethyl 4-piperidine sebacate, that's pretty high in ion intensity within the polypropylene extract and the leachate, along with a few plasticizers, fatty acids, one thing we also noticed was that there were quite a few compounds that were seen within the extract, but were not seen within our water leachates. So that may be a good direction for us to look at the compounds that were more likely to be found in the water for trends over time. And then those found within the sediment extractions, looking for those that are more likely to stay associated in the methanol extracts, as those compounds are more likely to stay associated to the plastic for better understandings of the fate of these compounds and these microplastics in general. To kind of hone in on some of the compounds I think that were really interesting, include the Tenevin 770 that I highlighted earlier, which is a UV stabilizer within the polypropylene and is a known long-term hazard to aquatic life within the water. And in the ergophos, there's also ergophos 168. It's an antioxidant found within plastic, and its degradation products are known to be mammalian cell suppressants. And that was found to stay associated to the plastic, so might be a good one to look for in the sediment. Within the polyurethane, there were these suspected isocyanates that are used in the production of polyurethane. And when these isocyanates turn into more like amines, they can also be more toxic. But the isocyanates themselves are also allergens and respiratory sensitizers. And then finally, the quaternary ammonium cation is a biocide and a surfactant, and also associated to being a skin and respiratory irritant. So the next question was, what's happening to these compounds over time and in the water of the mesocosm and of the laboratory leaching study? First, we'll highlight is the Tenevin 770 in the polypropylene. On the left is the laboratory controlled leaching study, and it's showing normalized peak area. It's normalized to the internal standard for purposes of understanding the concentrations. And you can see over 3 months within the laboratory study that there seems to be somewhat of an increase in the first few weeks and a slight decrease towards the end of this Tenevin 770. And the UV exposure seems to enhance the amount being released of this compound. And then when you go to the mesocosm leaching study over that 1 year, you can see that the compound is present for the first month or two, but is no longer detected in the water after 3 months. So very interesting trends that kind of differ. And this compound was confirmed with the reference standard, so is definitely in the sample. The other compound is its transformation product, the hydrolysis product of the Tenevin 770. And it has a relationship where it's steadily increasing over time and also enhanced by UV light exposure. For the mesocosm leaching study, you can see it mainly within the first month, and then it's again no longer detected after 3 months. And then the next question is, what's happening for samples like in the polyurethane? So this compound, which I'm still working to better identify, is the C8H8N2O2, and it has an opposite relationship with UV light, where no UV light exposure actually increases the amount found in the laboratory leaching studies. And in the mesocosm, it seems to be steadily present throughout those 12 months, but of course, still decreasing over that time. And then for another compound, if you remove one C, one H, and one N, you get a compound that will not show up without UV light. Also a very interesting trend and very strong increase over those 3 months in the laboratory controlled study. And then also just seems to be present throughout the mesocosm leachates for those 12 months and might show a slight increase towards the end of the year. So the next question was trying to work to identify those two. I suspect that those two compounds are actually monomers and breakdown products of the actual polymer. And so I've been doing some proposed structures to better match and fish for these compounds to better elucidate them. But there are quite a few others that are also similar to these two that are likely associated to being polymer additive, well, just polyurethane degradation products and tinidin degradation products to better identify. So findings and next steps. Well, first, one of the big findings was that the polypropylene seems to definitely have a lot more organic additives that are available in water than polyurethane. And there are multiple different types of polymer additives that were found within both polypropylene and polyurethane. But the really interesting thing, I think, is the fact that some of them are more, or actually don't show up without UV exposure or are enhanced with UV exposure. And so there's quite a bit more work that needs to be done on identifying those compounds and determining the mechanism of actually their appearance in the water. And the trends of the disappearance of these polymer additives in the mesocosm is something that we think is more likely to indicate degradation of the polymer additive or even removal by absorption, or just the movement of these microplastics towards the sediment. And so further analysis of those sediment samples is what I'm working on now, and will better elucidate the fate of these microplastics and of the polymer additives associated to these microplastics. And so that's the summary of at least the first two chapters of my work. But what I'm really working towards is really understanding the relationships with nanocomposites to the release of polymer additives, also modeling how different environmental stressors affect the release of these polymer additives, to providing even novel techniques and methods to identify these chemicals that are potentially harmful for environmental health and human health in our freshwater environments. And so with that, I would like to thank my funders, BSF and SAINT, and give an acknowledgement to my lab, especially my advisor, Lee Ferguson, and the Ferguson Laboratory as a whole, along with all the other labs that have made these projects possible and have supported me to give me the results that I can share with you all today. And so with that, I will stop and let you all ask questions on anything and everything plastics.
Thank you, Amari. That was excellent. Really appreciate that.
Of course.
At this time, I'd like to open it up to questions from the audience. I have lots of questions, but I'm going to wait to nerd out. Anyone from the audience, please either type in your question or just type in your name and we will call on you if you have a question. Can y'all hear me?
Yep. Oh, hold on. Let me, Jonathan Lucas. All right. Jonathan, you're unmuted.
Okay. Can you all hear me?
We can.
Yeah.
Okay. Hey, thanks for that, Amari. I wanted to ask, it looks like the carbon nanotubules do absorb the plastics or the polymers. And so they, I guess, technically inhibit the release into the environment. But is that really, in the big picture, an environmental gain? Because, I mean, those carbon nanotubules full of polymer are still out in the environment. You know, they didn't actually get rid of it. They just absorbed it into a different location. So is that really, you know, how much of an environmental benefit is that really?
Yeah, yeah, no, I definitely agree with you there. And I don't think that, I think the concentrations that I was still seeing in the water were still significant and problematic for environmental health and harm. And I didn't expand to even larger concentrations of CNTs, but yeah, I think there's more than just the concern for BPA or tert-butylphenol. Those are only two additives that I studied. There might be more that have different relationships with CNTs and the polymers that are, you know, enhanced or have no effect with CNTs and these polymers. But, you know, it's still problematic. I'm not encouraging, you know, polymer producers to start throwing CNTs and everything to fix our problems, because I think that's a short-term idea when the larger problem is that we're overproducing a lot of unnecessary plastic that has way too many different combinations of chemical contaminants that are, you know, can be pretty problematic. So yeah, that's a really good question.
Thanks.
Thank you, Jonathan. Do other folks have questions? I think we've got a mix of people from academia and industry here. Well, I'm going to go ahead and ask my question because there's no time like the present. Amari, I was really fascinated by the comparison of the outdoor mesocosms with your laboratory incubations, and not knowing much about the Duke field site or the environmental area, is there a lot of natural dissolved organic carbon, humics, those types of substances in the mesocosms that are out in the field that might be offering, you know, alternative binding sites?
I mean, the water is pretty turbid. If that's the big question, yeah. I did not study the DOC content of the water, but I would suspect that there's quite a bit of it that allow for different absorption of contaminants to it. So it's, yeah. It's
okay. Okay. So were your samples, those mesocosm samples, were they like 0.2 filtered, or were you running them? I missed that part, I think.
Yeah, the water samples were first filtered through GFF filters, and then they underwent solid phase extraction.
Okay, 0.7 GFF, 0.7 micron.
It's it might be 0.7. I thought it was 0.2. Yeah, but it's around that range.
Okay, we found that 0.7 actually. So I have a student working on rainwater DOC samples, and we found that 0.7 actually does not do a great job of keeping out all DOC, and actually is very inconsistent in the amount of DOC it lets through. So we've switched to 0.2, and I think that's because of colloids and colloidal shape, colloidal phase DOC. So we've switched to 0.2 for that reason. For any of our, you know, dissolved phase analyses, and seeing more consistency. So yeah, so that's interesting. So I've never seen that setup. I'd love to check that out sometime. Yeah,
it's interesting that we were the last project for the mesocosm, so it's a little sad. But you know, I think they're a really good example of looking at, you know, miniature environments to see what's happening in systems, and especially if you analyze all the different compartments, whether that's snails to fish, if you can. That's just a large project in itself, but at least, you know, the water and the sediment stories allows for a very interesting understanding of, you know, how long does it take for these microplastics to settle or you know, move somewhere else, or different compartments. So I liked it.
Okay. And if I could ask one more question, if that's all right, unless someone else from the audience wants to jump in. I kind of wanted to know about your mass spec, the UPLC, and be brutally honest, in a given 365-day year, how many days does it break down?
Ooh. I don't want to wish evil on it because it's still running for me tonight. I don't think it breaks down that often, but when it does, I mean, at least a couple times a year, when it does require quite a bit of time to get it back up into condition that I want it. So at least maybe 3 or 4 times for the Orbitrap, and then for the pumps, I think it's mainly just old age, that, you know, there's just different maintenance that is required for pump seals, and, you know, being a good plumber, which just takes a lot of time and a learning curve. But yeah, keeping that happy is hard. And I think that's usually on grad students to figure out quickly.
All right, thank you.
Thank you.
Any other questions from the audience?
Happy to cover anything, whether that's policy or science communication or just plastic. Do my
I
best.
guess a big question, plastics wise. I don't know if you heard the report on NPR, maybe it was a month ago, about, and you showed the same thing about how little of our plastics are truly recycled. Is there an initiative to change that, and why are some other countries, like European countries, so far ahead of us?
I mean, it's a pretty complicated question, just because I think that we should be moving more towards a circular economy for plastic, where everything we use ends up being reused and put back into the system. But the initiatives that are out right now are like the Break Free from Plastic Act that came out in February of last year. It did not get very far in legislation. The main things that are occurring in the US that are big steps towards eliminating plastic waste are coming from local cities and states, especially California. The UC system, their universities have banned all single-use plastic from use on campus. That happened a few weeks ago. And then in New York, they're banning things like styrofoam, which releases, those harmful styrenes that are linked to cancer. But yeah, there are a lot of just mainly ground level, small local town movements to remove bags and other plastic items. But it really takes a larger, widespread initiative amongst industry and government and academics to solve those larger problems. I think some of that is just because we're trying to find alternatives. But most of the alternatives out there are what were around since before plastic existed. You just go reusable. It's just getting people on board with it. And sometimes it can start off being an inconvenience, but once the system is in place, it can be sustainable.
Thank you. I've enjoyed your talk. I enjoyed talking to you. I hope I see you at an ACS meeting in real life someday soon. I don't want to dominate any more of your time. I thank everyone for their attendance tonight. And I thank Amari for her talk and her time as well. And I'd like to thank Malcolm Barnard for organizing this, and Ryan, thank you very much for setting everything up for us on the IT side. This presentation will be available on the Eastern North Carolina American Chemical Society YouTube channel, which also will have a link to Amari's YouTube channel. And I urge you all to check those out. We were in planning stages to try to do some videos and also some Eastern North Carolina ACS trivia. And so stay tuned for some of that. And with that, I thank you all, and I hope you all have a very good night, and try not to use plastic for at least a week.
Thank you.
Thank you again, Amari.
Good night.
Thanks, y'all.
Good night.
Hey.